So in this video, we're going to talk about relations and functions. So probably one of the simpler definitions that you get in math is a definition of a relation. And by relation, we just mean any set of ordered pairs, period. That's all it is. So if you've got a set of coordinates, first coordinate comma second coordinate, then that is a relation. Usually we will refer to this as a binary relation, and if you want to talk about more advanced types of relations, you can take a higher level math class for that. We're only going to be concerned with binary relations, so ordered pairs. All right, so here's an example. Here's a relation I'm naming R. We have ordered pairs 1, 3, 1, 4, 2, 7, and 3, -6. That represents a perfectly fine relation. Sometimes relations are a little bit more complicated. You can write it maybe in set builder notation rather than just listing out the ordered pairs. Sometimes it's just impossible to list out all the ordered pairs but still have a relation. So one of the things that helps us with relations sometimes are just graphs. So in particular, here's another example of a relation. Let's say S is the circle centered at the origin with radius 2. That also represents a relation. The graph here that we have for the circle, I know it's a little bit small, but this graph that we have here for the circle represents all of the points that are a distance of 2 away from the origin. You could write all those ordered pairs, like here we have the point 2, 0, here we have the point 0, 2, and lots of other options for points as you go around the circle. Again, we can't list all of those out, but we can describe it. You could describe it with an equation, but in general, this is going to be a set of ordered pairs, so that represents a relation. Things that we're interested about relations. Well, domain and range are huge concepts for relations. So for domain, we mean all of the x coordinates that we see in the relation. And for the range, all the y coordinates. So usually we say first coordinate and second coordinate, but we're thinking about these things typically in an xy plane where we think about the first coordinate of the ordered pair being the x coordinate, the second coordinate being the y coordinate. So I just defined it in terms of x and y coordinates. All right, so let's look at our relation R here. I see an x coordinate of 1. This also has an x coordinate of 1. This one has an x coordinate of 2. This one has an x coordinate of 3. So its domain is just 1, 2, 3. If I look at the y coordinates, we have 3, 4, 7, and -6 across those 4 points. So the range would just be those 4 values, and I just put them in increasing order by value. How about for the circle? Well, it's a little harder here, but for x coordinates, I just want to look at what coordinates are represented by this graph. I'm not worried about how far up and down the graph goes. I'm only worried about left and right here. What x coordinates do we see? Well, the lowest x coordinate that we see is -2. The highest x coordinate we see is 2, right? Anything in between these two is hit by some point. So the domain here will go from -2 to 2. Likewise, if we look at the range, we're only interested in the y coordinates, how far up and down our graph is going. Well, it bottoms out here at -2, it tops out here at 2, and we hit everything in between. So in this case, both the domain and the range of that relation are going to be -2 and 2. We use interval notation here to describe it, and we're using brackets to denote that the endpoints are included here. So this represents all real numbers in between -2 and 2, including -2 and including 2. A special type of relation that we talk about is a function. When we have a function, we mean that an x-coordinate is paired with exactly one y-coordinate. In the previous example, neither are functions. Let's see why. Let's scroll back here. Here's an x-coordinate of 1. It has 2 y-coordinates associated with it. That means it's not a function. When you plug one thing into a function, you have to get one thing back out. This one says if I plug 1 in, I get 2 different things out, 3 and 4. Likewise, for the circle, this is also not a relation. Notice here for the point at the x-coordinate of 0, there's a y-coordinate of 2 and -2 in the relation. So neither of these two things are functions. And those words are literally what I just said. Well, there's something, when we have the graph of a function, there's something that helps us be able to determine whether or not something is a function, and that's what's referred to as the vertical line test. Let me scroll back really quickly here to that previous example with the relation s. Notice I started here with 0 and said that we had the point 2 and negative 2 for the y's was associated with the x-coordinate of 0, and that's why it wasn't a function. Well, notice here the y-axis is a vertical line, and it hits the relation in 2 spots. That means that that one x-coordinate had 2 y-coordinates associated with it, which means it's not a relation. So that's exactly what the vertical line test says. It says that the graph represents a function if and only if every vertical line intersects the graph at most one time. Now, it may be possible where the vertical line doesn't intersect the graph at all, but if it does, it can only do it once. So over here, notice that if we look at the far left or far right, it seems like the vertical line test is being satisfied because vertical lines over here only intersect the graph one time. However, notice it says that every vertical line intersects the graph at most once. And in particular, we've got lots of vertical lines here. The y-axis will do the job, but lots of vertical lines in this region that cross the graph 3 times. That's definitely more than once, so that means that this relation is not a function. Let's look at this graph, though. And this is where the at most once piece comes in. Over here, vertical lines don't cross this graph at all. That's okay. We don't care. It says that if it intersects it, it does it at most one time. So if it intersects it once. It could intersect not at all. Okay. Over here, we look at vertical lines going straight up and down, and we only hit the graph one time. So this does represent a function in this case. All right. So one of the things that we're going to need to do when we start dealing with functions is a way to describe them algebraically so that we can do algebraic manipulations and do some different types of analysis on them. And that's not just important in this class, but in any math class going forward. So what do we mean by function notation? Well, a lot of our relations end up being equations that involve 2 variables. We have an x and we have a y. So usually in that case, one of the variables represents the domain, whatever we're plugging into the function, and one of them represents the range, whatever we get out of the function. In most cases, we think of y as a function of x, which means that the x is the domain. That's the piece that's the variable we're going to plug numbers into. And the y is representing the range. That's the numbers that we're going to get out of the function. Some other way to say this is that the x is the independent variable, and the y is the dependent variable, because we may have independence for what we can pick for x, but once x has been picked, y is determined. All right, let's look at a simplistic example here. Let's look at the equation 2x minus 3y equals 6. You should represent this as an equation of a line. And certainly if we graph that line, we got lots of ways we could graph the line. Probably the easiest way here, since I'm not solving for anything and don't have it in slope-intercept form or anything like that, is that the x-intercept would be 3. If I plug in 0 for y, I get x equals 3. The y-intercept is negative 2. And then we would just connect those dots. But in particular, if we look at vertical line test, any vertical line here only crosses the line one time. So that we really do get a function. All right, so again, we're thinking of x is what we plug in, y is what we get out. So if y is supposed to be what we get out, we're going to solve for y. And then we have a y equals idea here. So the x is the independent variable, what we're going to plug in. We do all of the arithmetic that is involved when we plug in some value for x and get out a value for y. So if we solve for y in this case, we would move the 2x to the other side and divide both sides by negative 3. You would get 2/3 x minus 2. And again, the way we have this written, we plug in a value for x, do this arithmetic. Whatever the value is, we would multiply it by 2/3 and subtract 2. and then the y value is the output. All right, so what we do for function notation is basically we take out the y and just put in this notation, f and then an x inside parentheses. This is not multiplication. This is read f of x, and this notation means whatever we put in for x here in the parentheses, we're going to put in for x over here on the right-hand side. So let's say we want to know what happens when we plug 6 in for x. Well, the value of the function, in that for when x equals 6, we denote it with f of 6. We replace the x with a 6. So to get the value of f of 6, we just take out the x, put in a 6, and simplify. 2/3 of 6 is 4, minus 2 gives us 2. Let's look at another example. Let's say we have the function f of x is equal to x squared minus 4x plus 1. And this problem asks us to do 3 different manipulations with the function. We want to do f of 1, f of c, and f of the quantity x plus h minus f of x. So again, all f of 1 means is we take out the x and put in the 1. So everywhere we see x here, we're going to put in a 1. So f of 1 is 1 squared minus 4 times 1 plus 1, which gives us negative 2. F of c, well, we're just going to take out the x and put in a c. We'll get c squared minus 4c plus 1. And there's not a lot else we can do because we don't know what the value of c is. Lastly, this one's a little bit more complicated. The first thing I'm going to do is just figure out what we get when we put in f of x plus h. Now again, this notation means wherever it does not say take f of x and add h to it. That is not what this notation means. Whatever is inside the parentheses, you're going to take out the x and plug in what's in the parentheses. So f of x plus h, we're going to take out the x, put in x plus h. So we get x plus h quantity squared minus 4 times x plus h plus a 1. If we distribute here, this we would distribute out, we'd get x squared plus 2xh plus h squared. This one we will distribute the negative 4, so we get minus 4x minus 4h and add a 1. Now to be able to do the simplifying here that we were asked to do, f of x plus h minus f of x. Here is f of x plus h. Here is f of x. Actually subtract the polynomials, and you'll get 2xh plus h squared minus 4h. We talked about domain and range for relations. Let's talk about domain for functions right now. Remember, domain is the set of things that are the first coordinates or the x coordinates. So for functions, what are we allowed to put in for x to make sure that we get something out that's defined, something that is a real number? Okay? So let's look at an example here. We're asked, what is the domain of f of x equals 1 over x minus 5? Well, what can go wrong here if I plug in a number for x? Well, if I plug in a number for x here, this denominator could turn out to be 0. And we know that division by 0 creates an undefined situation. So if we plug in anything other than 5, we're good. But however we plug in 5, we will get something that's undefined because we get a 0 in the denominator. So in words, our domain is every real number other than 5. If we want to write this in interval notation, we would go from negative infinity up to 5, union 5 to infinity. Notice we have rounded brackets and not square brackets here because we definitely do not want 5 included. And remember, infinity is not a real number, so we never put a bracket on the infinity. Let's look at another example. This one's asking us what's the domain of g of x equals the square root of 15 minus 5x. And again, when you're looking at domain, you're asking yourself, what can go wrong? What bad things can I plug in? Well, in this case, we're doing a square root. At least in terms of the real numbers, bad things happen when you plug in negatives under a square root. So g of x will be undefined. Everything we're going to be doing here for the time being, we're going to be doing in terms of the real numbers. So it's really probably better to say that it's not a real number. We actually can define square roots of negative numbers. They just turn out to be complex. But for our purposes, they'll be undefined as a real number. We cannot take the square root of a negative. So if anything is under the square root is negative, that's any value for x that's going to put a negative under the square root is not going to be in the domain. So what we need is that what's under the square root, the 15 minus 5x, we need that to be non-negative, greater than or equal to 0. So solve this inequality for x. We'll subtract 15 from both sides, divide by negative 5, and remember when you divide by a negative, it flips the inequality, so we get x is less than or equal to 3. So in interval notation then, we have everything up until 3. 3 is included in this case, so we use a bracket on the 3. So we have the interval from negative infinity to 3, and then a bracket on the 3. One last example here. Let's put these two ideas together. We're asked, what is the domain of h of x equals square root of x plus 7 divided by x squared minus 6x plus 8? Well, this has two things going on with it. We can't have negatives under the square root, and we cannot have zeros in the denominator. So let's handle them piece by piece. Making sure that what's under the root is not negative, we need to make sure that our x plus 7 is greater than or equal to 0. So solving for x, we get x is greater than or equal to negative 7. For the denominator, we need to make sure that's not 0 as well. So we're going to solve the equation x squared minus 6x plus 8 equals 0. And then we're going to exclude those x values. This x squared minus 6x plus 8 factors into x minus 2 times x minus 4. And we see then that the solutions are x equals to 2 or 4. So what we have then is we need x to be greater than or equal to negative 7, but also it cannot be 2 or 4. So if we're going to put that in interval notation, we're going to go from negative 7, include the negative 7, up to 2, can't include the 2. Keep going from 2 up to 4, can't include either the 2 or the 4. And then go from 4 to infinity, and again, don't include the 4.